Hello everyone, let's continue our revision. So the next topic or next chapter is on evaporation system. Okay, so in the evaporation process in food industry, commonly the process is used to increase the concentration of dilute liquids. Okay, where we evaporate the water. Okay, we heat the solution and evaporate the water to make the concentration of the solution higher after evaporation. Okay, so we have gone through some introduction on the process of evaporation, and we have introduced several types of evaporators, different design of evaporators. So this table actually is a summary of evaporators. Okay, they are a common application, their advantages and disadvantages. Okay, so let's start with the first one, rising film evaporator. Okay, rising film evaporator, it can be like horizontal type, like showing in the figure here. Okay, it's commonly used for fruit juice, dairy product, heat sensitive liquids. Okay, so it has a the product has short retention time inside the evaporator, good for heat sensitive foods, high heat transfer coefficient. Okay, but however, it's not suitable for very viscous liquid. Foam forming can be an issue inside the evaporator, so it may cause problem to the evaporation process. Okay, now the next second type is called falling film evaporator. Falling film evaporator is like a liquid. You can see in the diagram here, liquid is falling through the film here. Okay, so it's forming full film on top of the tube. So it's commonly used for milk, whey, juices, concentrates of different types of herbal extract or any plant extract or any other juice. Okay, so very efficient heat transfer, uh, gentle on heat sensitive products. Okay, yeah, same thing, has a low resident time. Okay, short time, the product has a short time staying inside the evaporator. Okay, but it's actually a more complex design, required good liquid distribution inside the evaporator in order to have good heat transfer. Uh, it is sensitive to fouling at low flow rates, because we know when the flow rate is low, so the high chances of getting burned or getting heated, overheated surface that cause the product to burn and stick on the surface of the heat exchanger. In this case, is the evaporator. Okay. Now, next we look at forced circulation evaporator. Okay. You can see the design in the figure here. We can use a pump to force flow, to circulate the liquid inside the evaporator. Okay, with the circulation inside the evaporator, so it's definitely it will have a better heat transfer rate. Okay, now normally it's used for tomato paste, sugar solution, viscous liquids. When we have a particle liquids or you have a viscous liquid, okay, it's always preferable to use a forced circulation types, which in this case we have a pump to flow the viscous liquid in the evaporator. So it's good to handle high viscous products, resistant to fouling, okay, because we have a high flow rate, so the contact time of the product with the heat transfer area or heat transfer surface is short, so the possibility of get fouling is lower. Good for crystal forming solution. Okay, if you are planning to have crystallization happens inside. Okay, before the crystallizer, maybe we can initiate the crystallization process, so it's good to have the liquid to use this forced circulation evaporator. Okay, but however, the disadvantages of this type of evaporator is that it requires high energy consumption. Okay, you need to use pump some more. Okay, higher operational costs. Okay, because we have more mechanical parts. We need more energy, more maintenance. Okay, more with more of the operating required materials. Okay, so the cost is higher. Next is agitated thin film. Okay, so it's something like sculpted surface heat exchanger. We have agitator inside. Okay, so it's used for highly viscous or sticky product. Example, honey. Okay, some of the plant extracts, enzyme mixture. Okay, very sticky, very high viscous, high sugar content. Usually it's very sticky, or high starch content, so very sticky. Okay, excellent for very viscous and sticky material. Very short retention time inside. Okay, because we have a agitator that can generate turbulence inside the evaporator. It helps to improve the heat transfer and also movement of the liquid, and also distribution of the material inside the evaporator. So we have very efficient heat transfer. Okay, very short retention time, minimum fouling because we have agitation. Okay, so the product won't stay on the surface for a long time. Okay, very quick. Can move around. Okay, so fouling issue is a minimum inside the agitated thin flame evaporator. Okay, next, the disadvantages of this type of evaporators. Okay, they are very expensive because we have not only the evaporator itself, we have to design with the agitator. Okay, so it may incur extra cost. That's why it's expensive. Limited capacity, so to have the agitator inside, we have a limited room to ensure it have a proper agitation, so the capacity is small. More complex to maintain. Okay, so we have more components as usual. We need more care, more maintenance, and more procedure and complex labor experience to maintain and to operate this evaporator. Okay, another one is a vacuum evaporator. Okay, if you can run the evaporation, it can be a single effect or multiple effect with a vacuum condition, vacuum evaporator. So it's suitable for heat sensitive products. Okay, when we reduce the pressure in vacuum, then the boiling point of the material can be reduced, right? So we can boil and evaporate the water at lower temperature. So especially fruits concentrate, flavor which is actually very heat sensitive, the aroma of the product, the phenolic compound, the bioactive compound that we extract from the plant, they are very sensitive to heat, thermal sensitive. So if you use a vacuum evaporators, so it's good because it can operate at low temperature, preserve the flavor, color, nutrients, and everything. Suitable for delicate products, which is actually expensive. Okay, certain extract, certain uh, compound which you want to isolate. So it become a, a good choice when we have a very expensive and a very uh, limited amount products. Okay, and its advantages are low evaporation rate. Okay, um, because of vacuum, so it actually we have to have a vacuum environment, so the evaporation rate may decrease. Okay, and the system to create vacuum inside the evaporator is expensive. The vacuum pump is very expensive, and the operation of the vacuum pump is expensive. So the whole design also require very special design. We have to ensure it's very enclosed. Okay, not only make sure it's very well sealed and make sure it's in vacuum condition, right? So extra materials to build the evaporator. That's why it's more expensive. Okay, so now we look at the methods to calculation methods involving single effect evaporator and multi-effect evaporators. Okay, well, we start with the single effect evaporator. Okay, so as I suggest, always we try to sketch our problem. Okay, so we illustrate the problem in a picture form. Okay, so in a single effect evaporators, we can sketch evaporators something like this. Okay, so we have two inlets usually. One is the feed. Feed is the inlet to the tank, to the evaporators. Okay, we should have the mass flow rate, the feed, F, the mass fraction of the solid in the feed, temperature of the feed. If you have temperature and you have uh, we assume it's atmospheric pressure, we can find the enthalpy of the feed. Okay, we have another stream of inlet, but it's not in contact with the product. We have a steam supply. Okay, so the mass flow rate of the steam, we use a S symbol, and then the the uh, pressure of the steam, temperature of the steam, and then we can find the latent heat of evaporation of the steam. Okay, at that temperature and pressure. Okay, so after the heat exchange, the steam actually release the heat to the product here. Okay, so after the steam release the energy or the heat to the liquid or the product inside the evaporator, the steam become a condensate. Condensation happens. Okay, when condensation we know, okay, it release heat, temperature will drop, so will form a condensate. Okay, so the condensate mass flow rate we can use S as the symbol because we assume the flow rate is still remain the same after condensation. Okay, pressure, temperature, and enthalpy of the condensate. All right, so the feed after entering the evaporator, it experience heating, right? The heat come from the steam. Okay, so it start to boil. Okay, so under steady state condition, after the process has stable, okay, so the P is actually the space, the volume space on top of the liquid is the pressure is actually the vapor pressure of the liquid here. Okay, so the liquid here actually we assume is at its saturation temperature, which is equivalent to the boiling point. T1 is actually boiling point of this liquid. Okay, then the pressure here is the vapor pressure of the liquid here. All right, so after heating, the liquid here actually start to boil, bubbles, and then it start to evaporate. Okay, form vapor. So vapor going out from the evaporator here, we use a symbol V to represent the mass flow rate of the vapor. Y here is the mass fraction of the solid inside the vapor, temperature of the vapor, and then um, enthalpy, okay, of the vapor. Oh, sorry, this one can be latent heat of vaporization, KHV. Okay, then after the evaporation, we have a concentrated product. We call it concentrate or the product of our process. Okay, we use the L here to represent the liquid phase, is a liquid state. Okay, XL is the solid content or solid concentration, mass fraction of the solid inside the concentrate. Temperature, we assume is same as the inside tank temperature is the boiling point of the liquid here. H is actually the enthalpy of the concentrate at this temperature, at this temperature. Okay, so generally these are the information that we need. Okay, we have to define all the information. Then it's good if you can sketch the evaporators like this, right? Then we can perform mass balance. Okay, two types of balance we have to do. One is on the total mass, the mass of the mass flow rate. Based on the mass flow rate, we balance up the mass flow rate. Okay, and then the solute mass flow, or the solid mass flow rate. So the fraction of the solid here times the F, and the fraction of the liquid here times the L. Okay, but we assume there is no solid here, so there is no solid in the vapor. Okay, now determine the boiling point elevation. Okay, if the liquid here experience a boiling point elevation or a boiling point rise, we have to use the during lines or Lorentz line chart. Okay, so some of the material may experience boiling point elevation as compared to the boiling point of water. Okay, so if there is no, then we directly use the temperature and pressure here to find the boiling point of uh, pressure here. You find the vapor pressure. We have a vapor pressure here. We can find the boiling point of the liquid. Okay. Then we have the boiling point. Usually we use the boiling point as our reference temperature or datum temperature. Okay. Then we can calculate the driving temperature driving force, which is our Q. Our Q. Okay. So make heat balance first before we calculate this. So this is a heat balance of the inlets balance with the outlets. Okay. So our feed times the enthalpy, steam mass flow rate times the lambda here, the latent heat, the capital H. Okay, and then our concentrate here times the enthalpy, and then vapor times the latent heat of vaporization. Okay, so this is the energy balance or heat balance. Okay, so uh, once we have this amount, okay, we can calculate the heat required for evaporation, the duty. Okay, so it's actually the vapor times the latent heat of vaporization. Okay. Okay, so calculate actually S, we can calculate the S is actually the steam, steam times the latent heat of vaporization. This is the energy. So energy come from here, come from S. Sorry, my typo here should be S lambda. Okay, so energy of the whole evaporator come from the steam. Right, so the required area we can get from Q equals to UA delta T. Coming from here, we know the S, we know the lambda, the latent heat of vaporization. Okay, we equal to this, and we can get the area. Okay, and then the steam consumptions. Okay, we can take the Q here over the latent heat of vaporization. So we know how much steam is required to evaporate the product, to concentrate the product. Okay, or you can use vapor over S, vapor for V over S. V over S also can give you the steam economy. Now we can calculate the steam economy. Right, so in total, this is the general step to calculate for single effect evaporator. Okay, so and then we proceed to a multi-effect evaporator. Okay, multi-effect evaporator, we can have more than one evaporator, two evaporator, three effect, two effect, three effect, four effect, and five effect, and so on. Okay, so there are two general configuration. It can be a feed forward. Feed forward means the feeds move from left to the right. Okay, where the steam also move from the left to the right. This is a forward feed, four effect evaporators. Backward feed for effect evaporator, where the feed is anti-direction with the steam. Okay, you can see here the steam is from the left moving to the right, and then the feed is from right moving to the left. So the feed and steam are in counter direction, which is a counter flow. Okay, we call it backward feed for effect evaporator. Okay, so calculation involved in multi-effect evaporator is quite not straightforward, quite challenging, quite challenging. Generally, you need to solve like this. We have to do the mass balance like what we do here, mass balance of the feed, and then we have to balance out the solid. Okay, and then effect of each effect temperature and pressure we have to determine. Okay, and then split the total temperature drops across effect. Okay, all the delta T, delta T1, delta T2, delta T3, delta T4, make sure is balanced. We have to find a balance delta T. Okay, energy balance in each effect. Okay, each effect we have an energy balance, and then we calculate the vapor produced per effect. So how many S here? So another S here, S2, S3, S4. Okay, the vapor is important. Then heat transfer area calculation. So I make sure if equally it should be in equal same almost identical same heat transfer area in area 1, area 2, area 3, area 4. Okay, steam usage and economy, we can calculate steam usage from the inlet and outlet of the fourth effect. Okay, we can know the usage. Usage, you have to Q total over latent heat of evaporation. Okay, so iterate if necessary. We have to repeat again and again until we get area when the area are very similar. Okay, or the delta T here we have to keep on changing. The delta T, we have to split the delta T between the four effects from we know the total delta T. Total delta T means from the inlet and outlet of the feed. Okay, so this is a general step. Okay, if you want to try, you can test the example in the lecture notes and also try the last question of the tutorial 7. Last question in tutorial 7 is on multi-effect evaporator. Okay, but I think it's a good experience. Once you understand the multi-effect evaporator, actually you understand the concept of the evaporator. Okay, so next we move on to food refrigeration. Food refrigeration. Okay, refrigeration is quite common. Okay, we know refrigeration requires cold environment, right? We need to store our food for longer storage, okay, and to preserve the food from deterioration or become spoilage. Okay, so to avoid food spoilage or food deterioration, we need to have food refrigeration, food refrigerator. Okay, there are a few types of evaporator and condenser. Okay, the evaporation cycle, okay, involve these two main heat exchanger. Okay, we need one evaporator and we need one condenser. Okay, at least in the refrigeration system. Okay, now there are a few types discussed in the lecture notes. Okay, you look at the first one here, the bare tube evaporator. It's just a tube evaporator. Okay, so we have a design like this. Plate surface evaporator, so in contact with the surface, okay, to evaporate. Okay, pinned tube evaporator. Okay, so and then shell and tube evaporator. Okay, we can use shell and tube heat exchanger to evaporate. Okay, so the gas actually pass through. Okay, the refrigerants. Okay, pass through the tube, pass through the surface, and then in the tube and in the tube shell and tube heat exchanger to change phase from liquid phase to vapor phase. Evaporation happens. Okay, when it change phase, it absorb heat, right? So this is the uh, heat exchanger used to absorb the heat. Okay, and then we have another one, condenser. Okay, so after the refrigerants evaporated, become vapor, and then we condense it back, become liquid, so you can recycle the refrigerant and use as a refrigeration cycle. Okay, now we can have air cooled condenser. You use air to cool the vapor and then you condense it back. Okay, or water cooled condenser, we can use cold water. It can be like a double pipe type. Okay, cold water at outside, inside is uh, the refrigerant vapor, hot vapor. Okay, or evaporative condenser. Okay, we have a fan here and evaporate. And shell and tube heat exchanger, we can have liquid flowing through or any heating medium, cooling medium, or shell and coil. We have coil inside, condenser. Okay, instead of tube, we have coil inside, spiral coil. Okay, and then double pipe condenser, Okay, so this is the most simple design, right? So these are the six major or six common condenser used in the refrigeration cycle. Okay, then we look at the mechanical refrigeration cycle. Okay, so on the right hand side top here, so this is the common mechanical refrigeration cycle. Okay, we have discussed this. Okay, if you look through here, so we have liquid coming in here to the evaporator. Okay, so liquid going yeah, liquid coming in, and then we have warm air flowing here, right? So the warm air is from environment that we want to cool down. Okay, so the warm air come to here, so the warm air will evaporate the refrigerants. So the refrigerants will absorb the heat from the warm air. So at the end, we get a cold air coming out from the evaporator here. So the refrigerants experience uh, evaporation here, absorb heat and evaporates. Okay, so and pass through the compressor here. We have a compressor here. The compressor will compress the vapor. Okay, so it become a high pressure vapor here. Okay, and then it pass through to the condenser. Okay, so we use water here, for example, water as a uh, cooling 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 medium. So the hot vapor being cooled by the water here. We are cooling water here, so the temperature of the refrigerant drops, and then the refrigerant release the heat, and then it start to condense, become liquid back, become liquid refrigerants. Okay, so here still at high pressure. Okay, we see this side all at high pressure. After the compressor is high pressure, and then there's an expansion valve. The valve can expand the uh, liquid, high pressure liquid, and then it become completely liquid, a super coated liquid, and then uh, it will come down here. So this side is low pressure side. Okay, again, you experience evaporation again. The cycle continue until the cooling temperature that we want. The temperature of this area has been reduced to the value that we want. Okay, so this process can be keep cycling. Okay, until we get the temperature that we want. Okay, so uh, one important measurement that we make for the refrigeration cycle is this pressure enthalpy diagram. Pressure enthalpy diagram, you can see here, y-axis is pressure, x-axis is enthalpy. Okay, so if we monitor the pressure here and the change of enthalpy here, okay, so we can plot this curve. We can plot this curve. If you observe here, okay, the point one will start from here. Start from sorry, point four. Point four is start from here. The arrow here. Okay, when the liquid is at the refrigerant is at liquid state. Okay, you pass through the evaporator. Okay, so the enthalpy will increase. Okay, because uh, it change phase, right? Enthalpy will increase, but pressure and temperature still remain the same. Okay, so uh, temperature and pressure remain the same, but the enthalpy increase because the refrigerants change phase. So now from liquid phase to vapor phase, okay, until reach here. Then we have a compressor here. Okay, enthalpy also increase because we increase the pressure. The compressor will compress and increase the pressure to point 2. Okay, so at the point 2, when you reach the point 2, so at the constant pressure, it start to condense. When you reach the condenser, okay, so the enthalpy drops. Okay, because it's changing from gas to liquid, enthalpy will drop. Okay, so this happen at the constant pressure and constant temperature because phase change happen. Okay, then from point 2 to point 3, phase change happen, and then from 3 to 4, it become completely liquid, completely liquid. Okay, so at the constant enthalpy, but pressure drop. Okay, because convert from liquid and go through the expansion valve. Okay, pressure will largely drop. Okay, so to calculate the load here, okay, at the condenser, the heat load, okay, you can calculate by multiplying the mass flow rate with the enthalpy at point 2 minus enthalpy of point 3. This is the energy, the heat released by the condenser. All right, and then at this point, 4 to 1, okay, this is at the evaporator. So this is the heat involved in the evaporation. So mass flow rate times the enthalpy of zero point 0.4 minus enthalpy of 0.1. okay, and then we have work done here because compression. Okay, so again we can multiply the mass flow rate and multiply by the enthalpy of zero point 0.2 minus zero point 0.1. This one will give us the work done by the compressor. Okay, so one important parameter to evaluate whether the refrigeration cycle is effective or not. We use a parameter called coefficient of performance, COP. COP is the ratio of a QH to the work done by the compressor. Okay, if at this value, this one over this one. Okay, or it can be the QH over QH minus QL. Or we can just directly use the enthalpy of 0.1 minus 0.4 over zero point 0.2 minus 0.1. Okay, so this one will give us the coefficient of performance, right? So the higher coefficient, the better is the performance, right? Okay, so this is what we have learned in the lecture. Okay, then last section actually we learn on food freezing. Okay, we know freezing can be important for preservation of the food, but it also can be important to create the texture, the structure that we want for the food. Okay, so there are many parameters or factors influencing the food freezing quality. Okay, the frozen food quality is influenced by first the freezing temperature. Okay, make sure the temperature is correct. The food size and thickness of the food. Okay, so this will definitely influence the effectiveness of food freezing. Food composition, how much water content and fat content and sugar content. Okay, because all these may influence, because sugar may crystalline as well, so it will influence the food freezing process. Fat also involved in the forming uh, layer that inhibits the heat transfer. Okay, and then the heat transfer rate, packaging and product arrangement. Okay, finally, if freezer type, what type of freezer we use? Air blast, plate, and so on. The type of freezer also influence the food freezing process. Okay, so these are the key 6 factors that I summarize here. Okay, now to know that, one thing we can do is we monitor the uh, temperature change in the food. Okay, let's say you see diagram here, we can identify the crystallization zone. We try to minimize the crystallization zone so that we try to minimize formation of a large crystal. Okay, so if you have a slow freezing, we'll get a large crystal in the food. Okay, so we try to make it fast or rapid. We have a rapid freezing, then we can minimize the size of the crystal, water crystal, ice crystal formed inside the product. Okay, so there are 2 lines here show when it's a fast freezing and slow freezing. Okay, so fast freezing, you can see the total time is shorter. Uh, Slow freezing, the line take longer time and the freezing time. So the graph here shows the y-axis is the temperature, x-axis is the freezing time. Okay, uh, you can see here. Okay, if you are fast freezing, the critical zone, the product experience critical zone as a shorter time as compared to slow freezing. They experience 6 hours of critical zone. Okay, and then you can see the freezing at beginning is very linear, right? Very fast, very smooth, very uniform until certain layer here it start to slow down. Okay, because at beginning the freezing involve the the outside of the material. Okay, so as time pass, get a thicker layer of ice form. Okay, so at this point, the freezing process becomes slower. Okay, okay, and same thing here. Okay, so we have a region here because at this region, not only for freezing, but it start to form crystal. Because the concentration of water is reducing. As more and more water convert become ice, the water available inside the product is become less, and then it start to form crystal when the concentration of water inside of the food become low, right? Then, so in this diagram it shows that freezing time play a very important role because it will determine our critical zone. Okay, so to know that, okay, we can predict the freezing time by using Planck equation or PAM equation. Okay, these two equations are important for us to predict the freezing time. The two equations are slightly different. Okay, pump equations, we have the enthalpy value and delta T value, which is said to be more accurate, and it needs a Boyd number. Okay, Boyd number is very similar to Nusselt number. The difference is that Boyd number is the ratio of the convective heat transfer coefficient times the characteristic length ratio to thermal conductivity of solid. In Nusselt number, the thermal conductivity is for fluid. All right. So when we have this two equations, we can predict the freezing time. Okay, with all the parameters. Be aware of the P and R, and the E value is the geometry dependence. It can be a slab or plate, cylinder and sphere. Three different types of geometry shape. It has a different value. Make sure you substitute the right value when you calculate the freezing time. All right. And last section actually we talk about freezing equipment. Okay, there are various type of design. It depends on the food products and what kind of freezings that we want. So the most common and popular one is air blast freezer. Air blast freezer, you can see here, you can have tray products are put, the products are placed on the tray and then on a trolley. We can push this one into the air blast freezer. It's like a room, Okay, we have a evaporator and condenser. Okay, that can produce cold air that can freeze and frozen the food. Okay, inside the air blast freezer. It can be a batch mode or continuous mode. You have a one door or two door, or it can be just push through. Just push in and one side in, one side out. Okay. Another type is a belt freezer. Okay, it can be a spiral type belt. Okay, it can be a horizontal belt. It can be a double belt. It can be different type of belt. So just to move the product around. Okay, this is spiral one. Okay, the product actually spin around in the belt. Okay, so that it can expose to the cold air uniformly. Okay, so we can freeze the product easily, get frozen product at the end. Okay, this is a belt type. Or we can have a fluidized bed freezer. Okay, so this one is good for individual freezing. Okay, quick freezing. You can individual quick freezing, a very short time of required. But the weakness of this freezer is we need to have small and uniform products. The product must be small and in uniform size and uniform characteristics. Then we can control the freezing time. Okay, so the product is actually the air is blown from the bottom vertically, and then the product is floating on top. Fluidites in the bed, and then it cool while it's actually in the air. Okay, the another type we call plate freezer. Plate freezer, you can have, you can see here, you have a multi-plate. Okay, and then the product is placed in between of the plate. Okay, so in between of the plate, inside the plate actually has the refrigerants flowing through the plate. The heat is transferred from the refrigerant through the wall of the plate and to the food products in direct contact with the plate. Okay, so there is a hydraulic system that compress the plate so that it has a close contact with the product where the heat can conduction by conduction heat transfer, the plate can cool the product effectively. Okay, in this way. Okay, so plate freezer is quite popular also, and for seafood, for fish fillets, so it's quite commonly used, and it's quite uh, require less space, okay, for freezing. Okay, another type we talk about is on a liquid food freezer. Okay, it's just like a, heat exchanger lah, big heat exchanger. It can be a shell and tube heat exchanger. It can be a scraped surface heat exchanger, types that can transfer heat effectively. Okay, if it's a very viscous and particulate mixture, maybe a scraped surface heat exchanger can be used as this liquid food freezer. Okay, so it can be a continuous process, it can be a batch mode process. Okay, so it depends on the liquid. So it's commonly used to produce like ice cream or all the cold confectionery sorry. Okay, liquid base. The last one, immersion freezer. Immersion freezer is just like uh, it's also like a free bed purpose for quick, okay, individual quick uh, freezing. Okay, so we can have like fruits, vegetable, one piece by one piece, uh, deliver through the conveyor, and then they are soaked inside the liquid refrigerants. So the liquid refrigerants, when in contact with the product, okay, the refrigerants will absorb heat from the product and convert to vapor. Okay, so the product will lose their heat and become cold and become frozen. Okay, so this way uh, we can make sure every piece is frozen properly. Okay, and this is quite popular for some heat sensitive material. Okay, so immersion freezer is quite common in the food industry as well. Okay, so generally these are the freezers that we have learned. Okay, make sure you are able to differentiate them and understand the pro and cons of all these freezer. Okay, the freezing equipment we are covered. So we have covered all the topics that we learned in this whole semester, a total of 7 chapter. So hope you are clear now. Okay, and then try all the tutorial question. Check back your quiz. Okay, and I have released the answer. Check back the score that you get and look at the answer. Okay, learn from mistakes that you make. Okay, I already give you the comment on your assignments. Okay, check back the assignments, my comment. If you have question, actually you are feel free to contact me. Okay, we can discuss through the email. Okay, so hopefully you have a clear picture of all the 7 chapters, and you have mastered the skill of calculation through the tutorial, and test your understanding through the quizzes. Okay, so I hope the whole teaching and learning process is good for your understanding on this subject. Okay, so I say thank you for your patience and your attention. Okay, thank you for listening. Okay, so I wish you all the best. Okay, I hope I see you in someday somewhere. Okay, so stay in touch if you are want to continue study or further study. Maybe we can discuss in future. All right, so all the best for your study. Okay, all the best for your final exam. Okay, happy studying. Okay, thank you. Bye bye. Bye. Okay.